Okay. And, oh, sorry, let me just make sure. So I was marking those late Friday night. And so one thing that I do want you to check is I posted the solutions. So the test one solutions are on Moodle. Now, one thing that I absolutely need you to check is, well, first, that the total at the bottom of the page makes sense. So how I mark is you all start at 100%, and then I take marks away. So you don't have to build up to 100% because that's harder. So there's usually some kind of a free marks floating around there with my method, but I prefer that. And so you'll see I've subtracted marks as I go. Okay. And then I put the total at the bottom of the page. So you'll want to check that. But then I transfer it to this table. Now, once it's transferred to this table, I don't go back and look at the pages. Okay, so sometimes if I'm in a hurry or whatever, then I write down the wrong thing in the table, but that's what I check later. So my checks don't really mean anything if I'm checking the wrong numbers. So if you have found an error, that's cool. If you found an error in your favor, don't tell me about it. But if you found an error, then let me know by email. Maybe show it to me first, and then I'll remember. But if you don't send me an email, I'll never remember to fix it. Okay, so that's kind of my to-do list. And so send me an email, and I'll fix it. Okay. All right. So the solutions are there. You can have a look through those. And don't worry, it'll be back to haunt you on the final exam, all those concepts. And so you get to enjoy it again. Picking up from last day, we have the printout from last day is up here. We talked about exponential functions and logarithms, and then we just started in on the natural log base e, which is, for me, my default log is log base e. And we also talked about the common log, which is log base 10, which we usually don't even write with a base. If it's just written as a log, then it is log base 10. And if you have ln, I usually do a script ln, it's log base e. So just two special cases, but all the log properties hold. And then at the end of the day on Friday, we said, try the rest of the booklet on your own, and then we'll go through it on Monday. And here we are on Monday, ready to go through it. Okay. If you need a copy of the formula sheet, I have copies up here which have the log laws and exponent laws on it. So that might be helpful. If you have to expand the natural log of e squared times the root of 1 minus x, so the first thing that we're going to do for expanding, we look for any sort of multiplication inside. This becomes the natural log of e squared plus the natural log of the root of 1 minus x, right? Multiplication inside the log is going to expand to addition of the logs. Any powers I can bring down in front by the log law. I guess we don't have names for them. It's the exponent property, but 2 times the natural log of e plus 1/2 times the natural log of 1 minus x. Why is it 1/2? We said, well, by those exponent laws, right? The root of 1 minus x, I can rewrite as 1 minus x to the power of 1/2. And then I have the power of 1/2 that I can bring down in front. Okay. Now, the last thing I can simplify here is this is log base e. This is log base e of e, which is equal to 1. Because e to the power of 1, because e to the power of 1 is equal to e. Right? We use that kind of chain link. E to the power of 1 is equal to e. And so, or you can just remember that if you have the base of the log and the same value inside, that's how you cancel the logs. You kind of get rid of the logs that way. So the natural log of e is just 1. And so you get 2 times 1 plus 1/2 times the natural log of 1 minus x. 1 minus x, there's nowhere left to go because addition or subtraction inside the log, there's nothing we can do there. We can only deal with multiplication and division inside the logs. And so there's nowhere left to go but 1 minus x. I'll clean that up. That looks weird. Questions about that one? Yeah. Oh, because I was being sloppy here. Oops. Because e to the power of 1 is e. About the next one, we have to simplify 2 times.
You took 2.
Oh, thank you. 2 times the natural log of e to the 3x plus 1 minus e to the log of 2x minus 3. And I confessed it last day, because the natural log is my go-to log, I often just call it the log, and I understand that's confusing, and I'm trying not to do that. But old habits, old academic habits. Okay. So first things first, what can I do? I could bring this coefficient of 2, I could bring it upstairs, but I see the natural log and the e next to each other, and so those are going to cancel. And same thing with e to the natural log, that's also going to drop down. Yeah. So we get, I'll rewrite it, 2 times the log of e to the 3x plus 1 minus e to the natural log of 2x minus 3. The log and the e effectively cancel. Why? Because if you have 2 times the natural log of e to the 3x plus 1, you can rewrite that as 2 times 3x plus 1 by bringing that power down front, and then times the log of e. But the log of e is 1. So if you see that the log of e is 1 and the power drops down, then that's going to save you some time. 2 times 3x plus 1. I'm fine if you are able to see that this just drops down, that's fine. That's almost where I would expect you to be, where you can just kind of see, okay, these cancel out. So then if you went straight to here, I'm fine with that.
Well, let's just say we're not.
Then
You would just use the formula.
yeah, then you can say, okay, this is a power, which I'm allowed to bring down in front by the log laws. And then I have the natural log of e, which you would then have to deal with and say, okay, well, that's 1.
It's just the longer way.
Yeah. And technically what I'm doing here, but I'm okay with this jump or this leap. And then by the same kind of idea, e to the log of 2x minus 3 is just 2x minus 3. I'm trying to remember what the log law is. Of course, I deleted them. Of course. Come on. Oh, it's because I have multiples together. Let's see here, equals 2x minus 3, since b to the log base b of x is equal to x is a log law. And it's the last log law on your formula sheet. So that's why it might be nice to have a formula sheet with you. That's why I brought some spares. This is a log law. And so we get minus 2x minus 3. Now all of a sudden I don't have any e's or logs or anything. I can simplify this, right? I get 2 times 3x plus 1 puts me at 6x plus 2 minus 2x plus 3, bringing that negative inside. Collect like terms. 6x minus 2x is 4x plus 2 plus 3 puts me at plus 5. And that's it. That's all I can do. Yes? This one here. This one. Here. Here. Oh, this one, because there's a log law that says if I have b to the power of log base b, which I have, right? I have e to the power of log base e. So then the whatever's inside the log is going to drop down. So I'm just left with the whatever's inside, which happens to be bigger this time, 2x minus 3, but it's just going to drop down and cancel. So effectively, both of these just cancel in 2 different ways. Maybe I'll snag those log laws that we have. Thank you. Maybe I'll put these. I don't want. Just gonna remove this. Because these are the log laws. So besides the exponent laws, which are also on your formula sheet, I expect you to be fluent moving between these log laws. Yeah, that's just going to take some practice, right? But once you kind of practice it enough, they're really fun, and you can play the game. The only one we haven't talked about yet, but we will on the next page, is this change of base formula. All the other ones we've talked about, right? So the relationship between an exponential function and a log, right? We said they were inverses of each other. And then if I have multiplication inside the log, it turns into addition. Or if you're working the other way, you can zip it up into multiplication. You have a power inside the log, you are allowed to bring it out front, right? Which is really nice for trying to solve for something in the power, right? You take a log, then it brings it down out front. You have log base b of b to the x. These guys just cancel, right? Drop down to x. So these two I would call cancellation properties. B to the log base b of x drops down to x. And so this is how you're going to cancel exponents and logs. Same thing, division turns into subtraction, and we talked about y last day. And then this is the change of base formula, which we'll see on the next page. And moving between different bases. And I'm just going to do something kind of weird here and erase that because it's confusing. Okay. We have to solve for x in the natural log of the common log of x. What are we going to do? Is equal to 0. That's nice. Oh, first I'll fix this typo. Pretty sure it should be in. So if you have the natural log, by those cancellation properties, you have log base e, which means to cancel the log out, then you would need to raise it to the power of e, right? So you take both sides, e to the natural log, whoops, the natural log of the common log of x is equal to e to the power of 0. E is Euler's number, 2.71828, blah, 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 blah. But as long as you're doing it to both sides, you're allowed to do that. So now, bless you, by that cancellation property, e to the natural log is going to drop out. And what drops out? Well, the log of x, which is the common log, which is log base 10, is equal to 1, e to the power of 0. Anything to the power of 0 is 1.
But you can't do, you can just create a variable in front of both of the log, ln log x 0 as well. just put E.
Do you mean this E? So that's how we solve for things in the power or inside the log, is we raise it to the power of the base. And then we rely on these cancellation properties here, these guys. And we rely on this property b to the power of log base b of x gives me x, and that's how I'm going to chip away at what's outside the x.
I just understand that, but you can just put an E at the front. Probably right,
Well, it's not at the front. It's e to the power of log base e. Here. So here, I'm writing e to the power of log base e, and then I'm using that property. But as long as I do it to both sides, I'm allowed to do it. Sold. Sold. I'm going to do the same thing again. How? This is log base 10 of x. I need to get at the x. So as long as I do this, 10 to the power of the log of x is 10 to the power of 1, I can do that. They're still equal. As long as I do it to both sides of the equal sign, then there's still, the equality remains. So now, again, by the cancellation property, 10 to the log base 10 of x is just x. So then here, x is 10 to the power of 1, which is just 10. Not sold. Any questions about that one? So the trick is, if you're trying to chip away at something inside a log, you raise both sides to the base. Right? I'll even write a note. To solve for something inside the log, we raise both sides I want to say it's technically incorrect, but to the power of the base, but we raise both sides with a base of b. Got it. Yes. This one here. Because I ran out of room here, but 10 to the log base 10. So if it just says log, then it's log base 10 of x. So same method, right? 10 to the log base 10 of x just drops down to x because these guys cancel. But I had to do it to both sides, right? So I have it equal to 1 here, equals 10 to the power of 1. Nice. Okay. Old school calculators and many kind of non-engineering calculators still only have a log base 10 button and a log base E button. Okay. And so in those scenarios, it's useful to be able to move between bases, right? And so not just log base 10 and log base E, because we can have log base 2, we can have log base 8, 7, whatever base we want. And so the change of base formula is on your formula sheet. On your formula sheet, and it's that one that we've been kind of dodging. Yeah. E is Euler's number. It's the irrational constant 2.71828, blah, 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 blah. And it's just a number, but it's an irrational number, just like pi. So it keeps going forever and ever and ever, but it's got some special properties that we don't really need to know about here, but it is a common number that we use. And so log base E is really, really common that we use in science, especially. But E is just a number. And if you have your calculator, there's an E button always. On mine, I have to go to the red menu, the alpha menu, but it's down here at the bottom. And so you'll have E, so you can try it. E to the power of 1 is just 2.7182818, blah, 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 blah. It just keeps going and going and going. So you have an E button, I'm sure of it. Just need to find it. And so I guess it's on here, so I'm not going to write it out. Actually, I'll just, hey, yellow. Most calculators only have the natural log and log base 10. This is log base 10 of x, the common log. And so what could you do? As an example, if we want to write log base 7 of x in base 5, whoops, in base 5. So now I can say, okay, well, if I have log base 7 of x, but I want it in terms of log base 5, right? What can I do? I can let my my b be 7. So then I get log base 7 of x is log base 5 of x over log base 5 of 7. Or what if you want to write it in base 10 so that you can use your calculator? Log base 7 of x, then log base 7 of x is going to be log base 10 of x, the thing you're trying to solve for, divided by log base 10 of 7, which your calculator can do even if you only have log base 10 and log base e on your calculator, right? So a lot of these engineering calculators that look like this, kind of the Casio or whatever, have a little log empty base, empty inside log. So your calculator might have some log base button. If not, you'll need the log of the change of base formula, which is on your formula sheet, and that's why it's on your formula sheet.
Are we allowed to use that?
Yep. Yep. Maybe I should start taking charging commission on these Casio calculators. I don't want to use the change of base. It's not that bad, and it is on your formula sheet. And I'm not going to make you do it explicitly. It's just something that's good to have. So for example, this is log base 10 of 20, which we can use a basic calculator to check. And then same thing if we convert it to log base E, just to make sure that it works, even if we don't have the fancy calculator. So if we have log base 10 of 20, I'm going to write the base just to be explicit about it. You're allowed to write the base, it's just that we don't if it's log base 10. Matching log base 10 of 20. So now my B is 10 and my X is 20. If I want to rewrite it with log base E, then I'll write log base E of 20 divided by the log base E of 10, because B is 10 and X is 20. You can check on your calculator. Log base 10 of 20 log base 10 of 20 is 1.3010299996. Probably keeps going reasonably. But let's do log base E. So the natural log of 20 divided by the natural log of 10 versus the natural log of 20 divided by the natural log of 10, which is also 1.3010299996. So they're the same, and that's the point. Just keeping them the same.
Oh, there's no like breakdown. I think there's something for this question.
Yeah. I'm just showing how the change of base here, I'm just confirming on your calculator, but here, this is what we were doing, just using the change of base formula. Any questions about that one? Change of base formula. So that's the last formula in the logs on the formula sheet that we hadn't talked about yet, but now we know them all. What if you have to solve something like this for X? I've got 3 to the power of 2x plus 3 is equal to 5. How am I going to chip away to get to that X? The only way that I can do that is using logs, right? And so the only way to solve for X in the power is to use logs. So what log? It doesn't actually matter. What's the easiest log to use? Yeah. Log base 3, because we've got that cancellation property. Nice. Right? So I've got a base of 3 here. So if I use log base 3 around this thing, I would get log base 3 of 3 to the 2x plus 3 is equal to, don't forget, log base 3 of 5, because if you're doing it to one side, you have to do it to the other side. Otherwise, you lose that equality. Huh? So now, by that cancellation property, because I use the same log base as the exponential function, I have 2x plus 3 is log base 3 of 5. Log base 3 of 5 is just a number. So you can just treat it as a number. There's no x's in there. And so you can just use it as a number. Now, I'll write that. This is just a number. But I would prefer it if you just kept it as log base 3 of 5. Keep it exact by not finding the decimal version. This is just a number, but keep it in exact form. Exact form is when I don't do any rounding. I just keep it as log base 3 of 5. Huh? As long as I keep that as one thing, I can now chip away and find the x, right? I can subtract 3 from both sides, and then I can divide by 2 on both sides. So I get 2x is log base 3 of 5 minus 3. So x is log base 3 of 5, whoops, minus 3 divided by 2. Should be clear. So we have to use logs to get at something in the power, and that's the beauty of the logs. Okay. What about the next one? Here, it's less obvious which log base I would want to use, right? I've got 4 to the power of x minus 1, so I could use base 4, or I also have 17 to the power of x, so I could use base 17, or I can just do whatever log I want, right? And so because all the log properties are the same, so here we would need either base 4 or 17, or we can use any log. But most commonly we use the natural log, kind of ironically, because there's a common log. Or we can use any log. Most commonly, we use the natural log. ln. I'll clean this up, that says commonly. Okay. So we've got this 2 out front multiplying, kind of bunging things up. And usually if I only had an x in one spot, then I would move the 2 off of the x and kind of isolate the x in a way, or at least the 4 to the x minus 1 if this was just 17, for example, right? But in this case, I have x's in both places, so I'm allowed to just wrap both sides up in a natural log, which is what I'm going to do. So first I'm going to write this out. 2 times 4 to the x minus 1 is 17 to the power of x. So now, if I take the natural log of 2 times 4 to the x minus 1 is the natural log of 17 to the power of x. I take the log of both sides. We've got some simplifying we can do. I have multiplication inside my first log. I know the log laws tell me that, okay, I can kind of splinter these two and say the log of 2 plus the log of 4 times 4 to the power of x minus 1 teasing these apart. And as you get more comfortable, you would probably start to also bring down the powers in the same line, right? But for now, I'll do it on the next line. The log of 2 plus x minus 1 times the natural log of 4 is x times the natural log of 17. Now my x's are free to access, right? They're not in the power anymore. Now I can actually use them as x's, and I can collect like terms, and I can finally solve for x, which is nice. So I want to start moving towards bringing all my x's to one side and everything that's not x to the other side. And so the first thing I'm going to do here, of course, is expand this x minus 1 times the natural log of 4. So what do I get? I get the natural log of 2 plus x times the natural log of 4 minus the natural log of 4 is x times the natural log of 17. Because I like to have whatever I'm solving for on the left-hand side, I'm going to bring the x natural log of 17 over to the left, but also the natural log of 2 and the natural log of 4, they're just numbers. So I'm just going to bring them over to the right-hand side. And so that leaves me with x times the natural log of 4 minus x times the natural log of 17 is the log of 4, the natural log of 4 minus the natural log of 2. Just because I don't want to have more negatives than I need to. Right. I did the negative log 4 first. Now I can pull out the common multiple of x, finally, and I can get x times the natural log of 4 minus the natural log of 17 is the log of 4 minus the log of 2. depending on what you prefer, you might notice the subtraction of the logs of the same base, which means we can simplify those, right? Because that becomes division inside the log, right? So here I've got log base e of 4 minus log base e of 17. It's very important that they have the same base. But if they do, and I'm subtracting them, then I can zip those up and I can rewrite them as x times the natural log of 4 divided by 17. Same thing on the other side. The natural log of 4 over 2, or 2. Solving for x, I can divide both sides by the natural log of 4 over 17, and I get the natural log of 2 over the natural log of 4 divided by 17.
Or you can make it ln r natural log 2 minus natural log what?
No, you can't simplify. Are you trying to simplify this? We can't simplify. There's no way to simplify division. Division inside the log becomes subtraction, but division of the logs, you can't do anything. So then we're done. But that is just a number, which maybe I'll use Desmos this time to show it here. If I have the natural log of 2 divided by the divided by, can I add the division? No. Probably can fix it, but of 4 divided by 17. Completeness. I get negative 0.47905, blah, 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 blah. I'll bring that in.
What's that apple?
Desmos? Hey. Yeah, if you haven't used Desmos before, it's really good, but a lot of people only use it for the graphing side, but I actually think that the scientific calculator is pretty good too. But it's 2 different apps. So there's, this is the scientific calculator that I used, and then this is the graphing one, but they're both free. Where am I? Here. So approximately, but I would want the exact answer. So this is what I want. But to convince you that it is a number, and it is just a number, we did this. And it's missing a 4. Okay. Questions about that one? Ready for another? So if you want to get at something inside a log, How are you going to do that? Use the other cancellation property by taking the base of the log and raising it to the power of that base. The words are weird. In my mind, it's the power, but the power is the one up top. So using it as the base in your exponential function, technically. So the first thing that you'll want to do, though, is you'll have to isolate the log and just get one log so that you can apply the log base 10, for example. So this is 2 times the log base 10, and then you've got a log base 10 over here. But what you're going to need to do is you're going to need to bring all the logs to one side and possibly simplify them into one log, and then bring all the other things to the other side, right? All the non-logs to the other side. And so isolate the logarithm, which you might need to convert into one logarithm, and then convert into exponential form and then solve it. So what does that look like? Oh, before I do that, I want to add a page just in case. And how do I add? I want lines on here. Okay, just give me a sec. It won't let me add the lines if it's hooked up, but now it's not linked there. But now I have lines, yay. Oh. Yep. Before we keep going, I want to remind you of the quadratic formula. Does that probably ring a bell? I feel like, did we mention it last day? Review the quadratic formula. If we have something like ax squared plus bx plus c is equal to 0, that's a quadratic equation. Well, I guess the equal to 0 is not necessary, but this is a quadratic equation. And you might remember a parabola x squared looks something like this. And I can move it around and I can kind of have, have it in different places. I can have it like this, for example. So what am I doing? If I'm forcing this thing to be 0, I'm solving for the points, the values of x that make that function 0, right? So if I have this specific equation, which I can always force, right? Even if I don't have equal to 0 here, I can just move over whatever constant I have over to the left, and then I can make it 0 by subtracting whatever the constant is, right? So I can always create this quadratic equation. And so if we have this, then x is going to be negative b plus minus the square root of b squared minus 4ac over 2a. Probably rings a bell, hopefully. It is on your formula sheet. If I can find your formula sheet. So this is what it looks like on your formula sheet. So it doesn't give you the format of the equation. You're expected to know that. But if you have something ax squared plus bx plus c, and you want to find where does this thing equal 0, then you need to identify what your a is, what your b is, and what your c is. And then you can use the quadratic formula. It's also a nice way, or kind of a quick way of factoring, right? If you had to factor this thing, then you can find where it equals 0. We're not going to do any factoring, but we are going to use the quadratic formula. Okay. So just remember, always be on the lookout for something of this form, or if you can rewrite it as a quadratic equation, because then you can solve for the values of x that make that happen. Okay. Good. So that wasn't in the notes. I'm sneaking it in because we need it. We need it. What else do we need to remember? Recall that we can only take the log or any log of a positive number, so a non-zero positive number. Okay. And so we can only take the log of a non-zero positive number. We talked about that last day. So, but it's good to remember, because often if we're using logs, then what we're going to find is that we're going to have two solutions, but only one of them is valid because we can only take the log of a non-zero positive number. Yeah. We need to keep this in mind. When solving logarithmic equations. Now I think we're ready. I think what's kind of exciting, I just realized that might be the end of new things on your formula sheet. So that's kind of nice. Yeah, it is. Now we've seen it all. Seen it all. First thing that we're going to do is we're going to look at what values of x can I have, right? You could do it at the end if you wanted to. You can solve for x and see what's reasonable. But here, I can see that x has to be greater than 0. If you try taking the log of 0 on your calculator, it's going to return an error, math error or something like that, because it's illegal math. Math error. Still a math error. So then here, a little bit trickier. That means that 1 minus 2x has to be greater than 0. which means, okay, if I treat this, this inequality as an equal sign, just keeping an eye out for it. If you multiply or divide by a negative, then it switches the sign, right? And so I'm not going to do that. Instead, what I like to do is I'm just going to add 2x to both sides. That's allowed. So then I get 1 has to be greater than 2 times x. And now I'm dividing by a positive, which doesn't change the sign, right? And so now I get 1/2 has to be greater than x. Which means that the only values of x that I could possibly have is when x is greater than 0. So on a number line, I like to map it out. We have 0 and we have 1/2. So x has to be greater than, but not equal to 0. But then x has to be less than 1/2, but not equal to 1/2. So then the only overlap is between 0 and 1/2, not inclusive of either side. So we say the domain then is between 0 and 1/2. Round brackets because we're not including 0 nor 1/2. So very small domain. Okay. So like I said, you could do that at the end to figure out which answers satisfy the criteria. But I like to do it at the beginning just to get it over with because it's not that fun. But now we can start to solve this thing. 2 times the log of x minus 1 is the log of 1 minus 2x. Okay. First thing that I'm going to do is I'm going to zip up the 2. I'm allowed to zip up this 2 so it's not bothering me anymore and put it on the x, right? X to the power of 2. I'm allowed to rewrite that. Log of x to the power of 2 minus 1 is the log of 1 minus 2x. We need to deal with the 1 first, but in kind of a smooth move, I'm going to move this over to the left-hand side and collect my log base 10s. And I'm going to add 1 to both sides and move the 1 over here. Right. You could convert it into a log, but I wouldn't just because you're trying to solve for x. So then introducing more logs kind of just makes a mess. And so you can get the log of x squared minus the log of 1 minus 2x, which is equal to 1. Not yet. The quadratic. Not yet. You have to zip up these logs first. So because they're both log base 10, and I'm subtracting the logs of the same base, so then I can combine them with division inside. So I get the log of x squared over 1 minus 2x is equal to 1. Now I've isolated the log, right? And so here I'll make a note. Here I've isolated the log, which was a goal, right? Isolate the logarithm. You might need to combine the logs. And then we're going to convert it into exponential form, right, to use that cancellation property. And then we can solve. So this is log base 10. So then I have 10 to the power of log base 10 of x squared over 1 minus 2x is 10 to the power of 1. Making sure you do it to both sides. We use 10 so that they would cancel easily. So then I get x squared over 1 minus 2x is equal to 10. Now, starting to sense a quadratic coming my way, because what can I do? I can move this 1 minus 2x over to the right-hand side, right? Multiply it over to the right-hand side first. So I get x squared is 10 times 1 minus 2x. So then I get x squared is 10 minus 20x. Which I can then shuffle over to the left-hand side and set this equal to 0, right? Picking away at the minus 20x becomes, I add 20x to both sides, and then I subtract 10 from both sides, and then I'm left with 0 on the one side and a quadratic on the other. Now I have a quadratic. In this quadratic, A is 1, B is 20, and C is negative 10. You might still need to use your formula sheet, especially if it's been a while since you used the quadratic formula. So then I get x is negative 20 plus minus 20 squared minus 4 times 1 times negative 10. It's important that you have that negative on there over 2 times 1, because otherwise we could run into some trouble. Can't take the square root of a negative number. So then I get x is negative 20. Let's see here. Negative 20 plus minus the square root 20 squared is 400 minus 4 times negative 10 puts me at plus 40. But I wanna be careful. I'll write it out like this, so you can see it. Then I get negative 20 plus minus the square root of 440. Now my calculator just simplifies it to 2 root 110. So you could do that if you wanted to, or you can pull out a 4, a multiple of 4 inside, and then use those exponent laws. Either way, or just use the root of 440 on your calculator, that's fine too. So what you're going to find is you've got x is negative 20. I'm going to do minus the root of 440 divided by 2, and I get negative 10 minus the root of 110. And below it, I'll do the approximation. Negative 20.488088848. Or it's going to be negative 20 plus the root of 440 divided by 2, negative 10 plus the root of 110, which is approximately 0.48808884817.
Or the final answer.
The exact answer. Do you mean these two? No. Why? But you've got a calculator. But why not? Only one of these is in the domain. Uh-oh. So only one of these is the solution. We said, okay, x has to be between 0 and 1/2. Otherwise, it's going to be illegal math. And we don't do illegal math. So here, recall, the domain is between 0 and 1/2, which means that this is not in the domain. But this one is in the domain. Therefore, x is equal to negative 10 plus the root of 110, or if you prefer, 0.48808884817.
So I use a different logarithm formula to get that number.
Yep.
That's fine as long as you're getting the same answer with using this one.
Where do you mean a different log?
I log base 10 and raise the logs on both sides, and the log base 10 of -1, that log on the other side, and the left side doesn't have logs, you just have.
Okay. Just be careful. I can't really tell, but you want to make sure that you're not doing to one side what you're not doing to the other side. So you have to do it to both sides. As long as you do everything to both sides of the equal sign, then you keep equality, right?
Mine's long. That's
So there are a couple of different ways that you could do it. Either way, you probably ended up with a quadratic. Yeah. But, so a note about the quadratic. What time is it? 5:20. A note about the quadratic. Quadratic formula. If you have x is negative b plus minus the square root of b squared minus 4ac over 2a, all of a sudden you're dealing with this square root. Right? We have to be careful with square roots because I can't take the square root of a negative number, right? And so here, remember, we can't take the square root of a negative. There are instances where b squared minus 4ac is negative. If it's 0, well, let's talk about if b squared minus 4ac is 0, then I have negative b plus 0 divided by 2a. That's okay. I'm allowed to do that. Negative b minus 0. It just means that there's only one root, right? One value of x that makes this true. I'll add a page here. So first scenario, if b squared minus 4ac inside the square root is equal to 0, graphically what that looks like, it looks like this. Only one value of x makes the function 0. Makes the function 0. Gonna run out of room here. Makes, can I just do f of x? Only one value of x. I'm still gonna need more room here. Makes ax squared plus bx plus c equal to 0. That's okay, that's allowed. We already saw if b squared minus 4ac is greater than 0, then just in general, we're gonna have something that might look like this, right? Where there are two values, of x. Make ax squared plus bx plus c equal to 0. That can happen. It can be down, facing down if a is negative, right? But same scenario, it's going to cross the horizontal axis at some point. However, if b squared minus 4ac is less than 0, right? We can't take the root or the square root, right? We can't take the square root of a negative. So visually, what does that look like? That could look like something like this. well, maybe I just have quadratic like that. It's okay, just means that there's no solutions, right? There are no values of x. There are no solutions, right? And what we mean by that is there are no values of x that make ax squared, whoops, plus bx plus c equal to 0. So that's what that looks like. So it can totally happen where there are no solutions. Right? And how you know is from that square root. If you get a negative number inside the square root, then there are no solutions, which is why I said, okay, we need to be really careful with, because we've got -10, and the only reason this didn't become negative is because we have a -10 here making addition, right? And so something to look out for. Okay. Once you have your solutions, you can always plug them back into the original equation and make sure that they work. But let's do our last page here. What if we have to solve the natural log of 2x minus 1 minus 2 times the natural log of 4, which is just a number, which is 3 times the natural log of 2, which again is just a number. Okay. Let's see what we can do here. First thing that I'm going to do is I'm going to try to zip up my logs, right? And kind of consolidate all my logs. And step number 1 is to eliminate these coefficients. I'm going to bring these coefficients inside, try to tidy up these logs. So I get the natural log of 2x minus 1. I'm going to go for plus. How can I get a plus out of that? Plus the log, or the natural log, of 4 to the -2. And I can do that. Which is the log of 2 to the power of 3. Makes it easier. Because now I have a log base e and a log base e and another log base e. So what can I do? I can make this, rewrite this as 1 log. I could even bring this log over here, but let's not overdo it. Let's just deal with this side. There are a couple of different ways that you could go about doing this, but I'll keep the sides separate for a little bit. So I'm adding logs of the same bases, which means that I can rewrite this as the natural log of 2x minus 1 times 4 to the -2 is the natural log of 2 to the 3, which you can simplify if you want. Now I have natural, so log base e on both sides wrapping around everything else. So now I can take e to the power of both sides. So I get e to the natural log of 2x minus 1. And I'll just keep it as times 4 to the negative 2 for a little bit longer, is e to the natural log of 2 to the 3. Or 8 if you prefer. Now, we use e because it's log base e, so then I can cancel these, and all of a sudden, I'm left with 2x minus 1 times 4 to the negative 2 is 2 to the power of 3. I haven't simplified 4 to the negative 2 or 2 to the power of 3, just for some extra practice with exponent laws. Because now, even though you're totally allowed to if you want, divided by 4 to the negative 2. But 4 to the negative 2, I can rewrite in the numerator as 4 to the power of negative 2. So then I get 2x minus 1 is 2 to the 3 times 4 to the negative 2. Or 4 to the 2, if you prefer. Either way, 2x minus 1 is 128 because I have it pre-baked. So then 2x is 128 plus 1, which is 129, leaving me with x is 129 divided by 2, which seems to go to a nice number, 64.5.
I could cancel all these.
Once you get here, you can, yeah.
Yeah, I didn't know you could. I mean, I thought I could cancel out all the 3 of them, but I thought you can only do 1 on each side.
You sort of can, but then you're bringing in exponent laws, right? If you're doing e to the power of all of this, then you would break it down into e to the power of this times e to the power of this. If you break up the exponents. Like I said, there's a couple of different ways that you could do it.
So you can do, I thought you can do 1 on each side. You can do multiple times. If I do it 2 times on the left side with e.
So you can't do it 2 times. What I mean is you could have done e to the log of 2x minus 1 plus the log of 4 to the negative 2. And then by exponent laws, because I'm adding in here, that becomes e to the log of 2x minus 1 times e to the log of 4 to the negative 2.
Right.
I don't think that that saves you any work because now this cancels and this cancels, and then you're left with 2x minus 1. But it is totally, you can do that. I think
I think
kind of net zero difference in work. I'm going to remove this one though, because that might be confusing if someone's looking back. What the heck happened here? We've got our last one. I'm going to give you a clue. You have to convert this into a quadratic first, or it'll be easier at least. So here, notice we can rewrite this as a quadratic. If we let some new variable y, if we let y be what? Probably 2 to the power of x. So we're introducing this, 2 to the power of x. Is the sneaky part. So if I have 2 to the power of 2x, maybe I'll rewrite this as 2 to the power of x to the power of 2 by those exponent laws, right? That's the same as 2 to the 2x minus 2 to the x. My iPad's glitchy. Minus 6 is equal to 0. If I replace 2 to the power of x with just the y, I get y squared minus y minus 6 is equal to 0. You can keep it as 2 to the power of x, but I think it's hard to look at. So I'm just going to use the y instead in its place. And then once I've solved for y, which is relatively simple with the quadratic formula, then I have solved for 2 to the power of x. So then I can solve for x. So here, now I can say, okay, y is negative b plus minus the square root of b squared minus 4ac over 2a. A is 1, b is negative 1, and c is negative 6. Y is negative 1 plus minus the square root of negative 1 squared minus 4 times 1 times negative 6 divided by 2 times 1. Negative 1 squared is 1 minus 4 times negative 6. I'm going to go for the root of 25 in the interest of time. Negative 1 is 1. Plus minus the square root of 25 divided by 2. I'm skipping some math. Not really. Just enough. So y is plus 1 plus minus 5 divided by 2. So y is 1. I like to do the minus first, even though the plus is on top, because I like to do the leftmost side and then the rightmost side. And so 1 minus 5 is negative 4 divided by 2, which is negative 2. And then 1 plus 5 is 6 divided by 2, which is 3. So now, recall y is 2 to the power of x. And I'm really trying to solve for x. I've solved for y. So therefore, 2 to the power of x is equal to negative 2, or 2 to the power of x is equal to 3. Taking these, 2 to the power of x is negative 2. If I have to solve for x, you can do log base 2, but I always just use the natural log. So I'm going to use the log of 2 to the x is the log of negative 2. but I can't take the log of -2 because that's illegal math. This does not exist. So that can't be an answer. What if I move these over a little bit and I try the other one? 2 to the power of x, or 2 to the power of x is equal to 3. I'm going to use the natural log again, my go-to log, my favorite log. Now I can use that log and I can bring down that x in front by the log laws. X times the natural log of 2 is the natural log of 3. So x is the natural log of 3 divided by the natural log of 2. And that's the answer. What if you didn't want to use or using log base 2? Around the 2 to the x, then you would have log base 2 of 3. Well, you would get x times the log base 2 of 2, which is 1. So then I'm left with x is log base 2 of 3. So x is log base 2 of 3. Log base 2 of 3 by the change of base formula is the same as the natural log of 3 over the natural log of 2. Aha. By the change of base formula, the log base 2 of 3 is the same as the natural log of 3 divided by the natural log of 2. So the answers, therefore, the answers are the same. Ta-da! And I think that's all I've got. This feels like plenty. I posted assignments. They look big, but they're actually not that bad. They're just mostly quick little logs and exponents, little 1 markers. You can have a look at those. If you have any questions, let me know, but I'll stop this recording.